Hello everyone and welcome today to our study group. Before we start today, we decided to show a short overview of what we have talked about so far, how all topics are connected, and how today's topic fits into the big picture. So here you see the big picture. And so what we've done is, in the first session, Alejandro and Emilian gave a general overview of what a stochastic optimization problem is in general. So we have seen what typical models are that are commonly used in a stochastic optimization framework, for example, using expectation minimization in the objective, or having a constraint in expectation, or chance constraints, or having a multi-stage problem. And they also showed an overview of numerical models that can be used to solve stochastic optimization problems, for example, stochastic gradient methods, dual methods, dynamic programming, and many more. And one example we have talked about in more details was the news windows problem, which is one example of a stochastic program that has a closed form solution. So, and then in the last two sessions, David presented a convergence analysis in the context of adaptive algorithms. Adaptive algorithms have a general form called recursive identification. In part one, we have seen that it is difficult to show the convergence of the general algorithm analytically because of the recursion or the feedback in the formula. However, there are theorems that state that an ODE may be associated with the form of the general adaptive algorithm, and studying the convergence of the ODE is an easier problem than studying the convergence of an adaptive algorithm. And so in part two, those theorems were applied to and demonstrated on two specific problems. One was the transversal equalizer, and the second one was active noise cancellation. And both are based on a least squares algorithm, which fits the general adaptive form. So, and now, while the last two sessions were covering the convergence analysis of algorithms which have an adaptive form, in session 2 and 3, Shitong, Bijie, and me presented concrete examples of those algorithms. And so in our talks, we covered stochastic gradient descent methods. And the first part introduced the stochastic gradient descent method in general. We used the area of machine learning to demonstrate its performance, emphasizing that this method is to be preferred in situations where we have, for example, large data sets, just to save computational per iteration cost and to accelerate convergence. And it was also mentioned how to perform variance reduction, how to deal with overfitting. We also covered stochastic subgradient methods and talked about the Adagrat algorithm and stochastic mirror descent, just to give an example of how the general stochastic gradient descent method can be modified to deal with, for example, non-smooth data, or when we have non-IID data, or when we have additional information about the geometry of the problem available that we would like to exploit. And finally, we have also talked about stochastic gradient descent methods that use momentum, like Adagrat or RMS probe. And we have also talked in more details about the famous ADAM algorithm, which performs adaptive moment estimation. So what we have talked about so far falls in the category of stochastic approximation. And so the randomness here lies in the samples or the updates that we use to update our algorithm. And so now today, we start a new category which differs from what we have heard so far. And the topic is stochastic methods for global optimization. And now I'm handing over to today's speakers, Xintao and Javier.
All right. Well, thank you, Victoria, for your introduction. That was a very good presentation of what we've done so far. Right here, me and, well, Xintao and me will present stochastic global optimization methods. So our presentation is divided into these three categories. First, I'll introduce some problems that we might stumble upon when dealing with global optimization. Then Xintao will introduce some formalities on local versus global optimization and global random search. And then we'll go through different stochastic global optimization methods divided into these 4 categories. This is just one way of categorizing these methods, but there are many different ways to do it. So first we'll look into exhaustive search methods, which are pure random methods that try to cover the whole feasible set. Then sequential random search, where each iterate is chosen with using some random process, but using the information that we got already from previous iterates. And then we'll go conceptually through some more complex methods that fall into the categories of two-phase methods or population-based methods. So when we talk about global optimization, we can talk about either deterministic or stochastic methods. In the deterministic case, each iterate is chosen using some underlying theory that guarantees us some properties like global optimal solutions or some greater convergence properties. And these methods are designed for specific type of problems, so they have some requirements on the characteristics of the problem, such as the objective function and needing to be convex or continuous. So these methods are not meant to be used for any type of problem. They need to fulfill some requirements. On the other hand, stochastic optimization methods involve iterates that are chosen using some random rules. So they do not guarantee to reach a global optimal solution. They only have probabilistic guarantees. And since in these cases we have limited knowledge on the objective function, then these are meant to be used for any type of problem. However, we might stumble upon with problems that are related to difficult landscapes. This is related to the computational complexity needed for these methods to have probabilistic guarantees that we will reach optimal solutions. So one of these problems we might stumble upon is premature convergence. So in the case where our functions, our objective functions have multiple local optima, then if we use methods that are inspired by local search methods, they might get stuck in local optima. So, and since we have no big amount of information related to our objective functions, then we wouldn't know if the solution that our method gives us is local or global. So we need to take some countermeasures to avoid premature convergence. And some of these countermeasures that we can mention are random restarts, so trying out local search iteratively from random starting points, or using some methods to steer away from already explored areas so we can improve the probability of reaching different optimal solutions. And in this context, it's relevant to mention this balance between exploration and exploitation. So premature convergence shows up when we are doing exploitation, so finding local optimal values closer to starting points. But we need a correct balance with exploration so we can cover the whole feasible set. Other problems that we might have is ruggedness. So in this case, the gradient information that we might collect from evaluating different points is not useful because we have multipolarity and we have steep ascents and descents. So in these cases, countermeasure would be using large population sizes, so testing a different amount of starting points. Another problem that we might mention is deceptiveness, where we have a big region that has misleading gradient information. So algorithms might tend towards local optima and leave optimal results behind. And in these cases, these search algorithms might perform even worse than random walks. So countermeasures that we can mention from this are large population sizes again, and sampling bad features. So sampling values that are unintuitively, values that might reach better solutions. And this is kind of a worst case scenario when we have neutrality and we have an optimal solution that is very isolated. So when we are stuck in neutral areas or areas without much information, and then there is not enough information to make good next iterates. So these methods degenerate to random walks. and then they might fall into premature convergence or slow convergence in order to find this global optimum. So now the question is, if we have some different stochastic global optimization methods, then which one will be the best, which one we should choose? And the answer is that there is no optimization algorithm that outperforms all other ones. And this result comes from the no free lunch theorem that says that if we talk about a conditional probability of reaching a sample set, so a set of values that we want to reach, given an optimization problem and algorithm A iterated m times, then the sum of these probabilities over all possible optimization problems is independent from the algorithm that we choose. So this is the idea that this sketch is trying to show. This is just a very crude sketch of the idea of the no free lunch theorem, where each different line represents an algorithm. So for all possible optimization problems, different algorithms might have different performances, and they may be better or worse depending on the problem. So in order to choose a useful optimization algorithm, then we need to obtain the most knowledge we can from the problem as possible. So now I'll leave Jintao to show the next section of our presentation.
Yep. Thank you, Javi. So let's talk about some global random search algorithms. So first, let's look at global versus local minimization problems. The global minimization problem finds the global minimum of the objective function f in a feasible region X. So here M denotes the global minimum of the objective function. If the value of the objective function evaluated at X star is equal to the global minimum of the objective function, then X star is a global minimizer. There exists at least one global minimizer. And on the other hand, if there exists a neighborhood N of Z such that f of Z is less than or equal to f of X for all X in the neighborhood, then Z is a local minimizer of F. A local minimizer becomes the global minimizer if the neighborhood N is replaced with the whole feasible region X. If the objective function F has only one local minimizer in the closure of the feasible region X, then the local minimizer is the global minimizer as well. The corresponding objective function is called unimodal. And otherwise, if there's more than one local minima, we say that the objective function is multimodal. Classical optimization methods deal with local optimization problems. We frequently simplify the theoretical models to maintain the unimodality of the objective function. However, there are important applications where multimodal objective functions cannot be avoided. If there are several local minima, we often run the local algorithms from several starting points to find the best. But using the multi-start of local algorithms is not very efficient if the objective function has a large number of local minima. And in global optimization, randomness can appear in several ways. We list the main three sources of randomness. So first, the evaluation of objective function are corrupted by random errors. And secondly, the points where we evaluate the objective function are chosen based on random rules. And thirdly, the assumptions about the objective function are probabilistic. For example, the objective function is a stochastic model. And in this talk, we mainly focus on the second case, where random decisions are involved in choosing the candidate solutions. Global random search algorithms are global optimization methods where random decisions are involved in the process of choosing the observation points. Next, we discuss the basic ideas of global random search. We generate a sequence of random points where each point xi follows some probability distribution PI. The distribution PI may depend on the previous points and the evaluations of the objective function at these points. And the number of the points can either be deterministic or random, and may also depend on the results of the objective function evaluation at these points. Global random search algorithms have some attractive features. The structure of these algorithms is usually simple, and the algorithms are often insensitive to the irregularity of the objective function and the shape of the feasible region. They may also be insensitive to the presence of noise in the evaluation of objective function. And it is easy to construct algorithms that guarantee theoretical convergence. However, global random search algorithms have certain drawbacks. The efficiency of the algorithms often depends on a number of parameters, and the analysis on good parameter value is lacking. Another serious drawback is slow convergence, and we will talk about it in detail in the next few slides. So before we get into some specific algorithms, let us formulate some common assumptions about the objective function and the feasible region. These assumptions are needed for the global random search algorithm to work. So the feasible region X is a bounded closed subset of the real set. Here the small d is the dimension of the problem. And the volume of the feasible set is larger than 0. And the feasible set is a finite union of the sets defined by a finite number of inequality constraints, where the function small g are continuously differentiable. This assumption prevents fractal boundaries of the feasible region. And finally, at least a uniformly constant proportion of a ball centered at the global minimizer with a small radius must intersect the feasible region. So this assumption rules out the configuration shown in this picture. Random search algorithms will not be able to approach the minimizer if we are not using local descent, because the path to the minimizer is too narrow, and we cannot find a circle that has a uniformly constant proportion that intersect the feasible region. And here we list the main assumptions about the objective function. F can be evaluated at any point of the feasible region without error, and the number of global minimizers is finite. And F is bounded and piecewise continuous on the feasible region. And finally, there exists a positive epsilon 0 such that for all epsilon larger than 0 and less than or equal to epsilon 0, those level sets are closed, and the function f is continuous for all x in this level set. So this assumption ensures that the objective function is at least continuous around the global minimizer. The last two assumptions are weaker than the continuity of f. So if f is continuous for all x in the feasible region, then the last two assumptions hold. Next, we talk about a category of global random search called exhaustive search. The idea is that we test each possibility in order to determine the best solution. It is an exhaustive examination of all possibilities. We discuss a very simple global random search algorithm called the pure random search. The main idea is to generate n-candidate solutions from the uniform distribution over the feasible region and return the best solution. For pure random search algorithm, we need the objective function, the feasible region, the number of iterations, a convergence criteria, and a starting point in the feasible region. For each iteration, we sample a new candidate point from the uniform distribution over the feasible region and evaluate the objective function at that point. And we save the best found solution. And this whole procedure repeats iteratively. So despite its simplicity, pure random search offers an asymptotic convergence guarantee in a probabilistic sense. Remember the definition of the level set? The probability that the uniform sample of size n contains at least one point in this level set is given by this equation here. So this indicates that as long as the volume of the level set and the volume of the feasible region are strictly positive, pure random search locates an element with probability approaching 1 as the number of candidate points increases. However, pure random search has drawbacks. If the volume of the level set S is much smaller than the volume of the feasible region, which means that this term in the bracket is close to 1, then it takes many samples to find a solution with high probability. And secondly, it is not clear when to stop the algorithm because in practice, we do not know whether or when we hit the level set. And thirdly, if the feasible region is not convex, it is sometimes hard to uniformly sample from the feasible set efficiently. In practice, pure random search serves as a natural baseline strategy for minimizing an unknown black box function over bounded convex feasible regions. Well, next we talk about the sequential random search algorithms, where we utilize the information about the previous observation points. The pure adaptive search algorithm is a natural variation of the pure random search. We define this level set ST that contains all the points X such that the values of objective function evaluated at these points are less than the threshold CT. So instead of uniformly sampling from the feasible region X, pure adaptive search algorithm samples from the improving level set ST, where the threshold CT is set to the objective function value of the current point. So basically, pure adaptive search generates a series of solutions with strictly monotonic decrease in objective function value. And the rest of the algorithm is the same as the pure random search. So here is an illustration of the level set ST on a one-dimensional landscape. Since the threshold CT is monotonically decreasing, we gradually narrow the search region as the procedure proceeds iteratively until the stopping criteria is satisfied. Well, of course, the sequence of the objective function values converges to the global minimum much faster for the pure adaptive search than for the pure random search. The major obstacle preventing the application of the pure adaptive search is the fact that it is difficult to find points in the level set. The problem of finding points in the level set is one of the major objectives of all global optimization strategies. So in general, there is no effective way of generating random points from the improving level set, apart from using pure random search in the first place. Next, we introduce another global search algorithm called random covering. The idea is that we cover the feasible region with randomly placed balls of fixed radius r. So we first define this ball that is centered at the observation point xi with the radius of r. And this rho here is some metric on the feasible region. For example, rho can be the Euclidean norm, and then this ball here is a norm ball. We sample the first candidate point from the entire feasible region. Then we sample the next candidate point from the previous set minus the ball centered at the previous candidate point with a radius of r. Then the procedure proceeds iteratively. The stopping condition can be that we have a fixed number of iterations, or the entire feasible region is covered by the balls. The radius r of the balls determines the accuracy of the approximate solution. The idea of this algorithm is that we do not want the new points to be very close to the points where we have already evaluated the objective function. And in practice, we can use a taboo method to sample the candidate points. If a random point uniformly distributed in the feasible region falls within the distance of r of one of the previous accepted points, then this point is rejected. The objective function is not evaluated at this point, and a new random point is generated. Yep, so that's the idea of random covering, and Javier will take it from here to talk about other sequential random methods and two-phase methods.
All right, thank you, Yinta. All right, so from random covering, we'll go now to simulated annealing. Simulated annealing is a very popular stochastic global optimization method. But in order to introduce it, first introduce hill climbing, which is a local search algorithm. So in hill climbing, we pick starting points, and in each iteration points, we get a set of candidate points. This function over here, the mutate function, aims to represent the process of finding candidates from our current iteration points. This might be taking a step towards some direction, or sampling from a normal distribution, or some pattern search. There are different alternatives that gives us these candidates. So what hill climbing does is evaluates the candidate at the objective function, and if the value is lower than the value evaluated at the iteration points, then we update the iteration towards this candidate. Else it is rejected, and we keep going with the same iteration point. This, of course, corresponds to the minimization problem. Hill climbing is usually presented in a maximization problem context. So in this case, in hill climbing, we're accepting all candidates that gives us a better value for the objective function and rejecting all other points. However, if the mutate function over here is only testing values that are closer to our current iterate, then this algorithm will lead towards local optimum. So there are several possible improvements that can be made from here in order to improve our chances to reach a global optimum instead of a local one. Simulated annealing is one of those, and I will present it in the next slide. Other improvements that one might take are stochastic hill climbing, where the mutate function involves some stochastic methods. Random restarts that involves testing hill climbing for random starting points. Random walks that are also influenced by the choice of the process within this mutate function. And taboo search, or similar to random covering, where next iterates are forbidden to take some values that suggest that we will reach to the same local optimum values that we have already reached. So what does simulated annealing does, and how does it improve from here? Simulated annealing is an algorithm that is inspired by material heat treatment in metallurgy. So annealing in metallurgy refers to the process of heat treatment of metals when we wanted to the metals to become homogeneous or to lose air bubbles. Then we process this metal from a high temperature towards a lower temperature, but lowering the temperature gradually, and that gives us some guarantees about the quality of the resulting metal. So this metaphor of lowering the temperature gradually is used in this optimization algorithm. So what this method introduces is an acceptance probability that allows us to pick candidates that don't necessarily improve the value of the objective function. So this is presented here. The probability of the candidate points to be the next iterate is 1 every time that the function evaluated at the candidate is better it is picked. However, if the function evaluated at the candidate is worse than the function evaluated at current iterate, then we choose it depending on a probability that's shown here. It's an exponential where the exponent is proportional to delta f, that is the difference between the evaluations and the objective function, and is inversely proportional to a factor t, which represents temperature, and that decreases over time. So at the beginning of the iteration, we have high values of the temperature. That means that this probability over here gets closer to 1. So candidates are often picked even though the value of the objective function is not improved. However, as time goes on, the temperature gets lower and this probability gets closer to 0. So then we get stuck in some points and we do not accept candidates that gives us worse values. And the idea is that the process will end up tending towards a global optimum instead of a local one. So this concept is presented in this illustration where the temperature is decreasing over time and is shown a graph of objective function that has multiple local optima. So for example, at this point, we might have an algorithm that is stuck in a local optimal, but since the probability of staying here is not immediately rejecting any value that is worse, then if we take a step far enough from this local optima, we might get out this local optima and eventually reach a global one. So the algorithm is pretty much similar to the hill climbing algorithm. However, the difference is that if the candidate evaluated at the objective function is not better, it is worse than the function evaluated at the iterate, then I get a value for the temperature that depends on the current iterate, and I pick a random value from 0 to 1 from a universal distribution. And then if this value is lower than the probability that was shown previously, then I pick this candidate. So it has been shown that simulated annealing with appropriate cooling strategies will asymptotically converge to the global optimum. However, this depends on the cooling strategy or the rate of the decrease of the temperature. So here there is a balance between the rate of convergence or the convergence towards the global optimum. Other methods that we might mention fall into the category of two-phase methods. The two-phase stochastic global optimization algorithms follow this basis structure. And at step 0, all values are initialized and we get a starting point and a starting index. And then we go iteratively through these two phases, a global phase and a local phase. So in the global phase, we generate a subset of our feasible region according to a sampling distribution. And in the local phase, we generate candidate points from this subset of the feasible region. And if a convergence criteria is not met, then we update parameters, we update our index, and we return to step 1 and we iterate. So approaches that fall into this category are random restarts or multi-starts, where the global phase refers to the random starting points, and the local phase are local search algorithms from these starting points that might be hill climbing or simulated annealing for some of examples. And another approach would be clustering, where the global phase, we pick candidates using the local search information. So we are only picking starting points that are promising, that is, points that are not likely to lead to the solutions that have been already discovered. And lastly, we introduce population-based methods. In these methods, we have a set of multiple solution candidates that are iteratively refined, and the information is shared between these candidates. These population-based methods are usually inspired by biological processes, so they use their own terminology. So instead of talking about feasible sets and objective points and objective functions, they use terms like population and fitness and natural selection. So I'll present now some examples of these methods. One of the most popular ones are genetic and evolutionary algorithms, where they do metaphors related to natural selection and crossover and mutation. So The solution candidates are denoted as the population. For each individual on this population, we assign a fitness value that allows us to compare between them. This is not necessarily the value of the objective functions, since these algorithms are fitted for multi-objective functions. Then the fittest individuals are selected for reproduction, and new individuals are created from the mating pool. And so terms like crossover mutation, natural selection, survival of the fittest, these are terms that are used within the context of algorithms that fall into this category. Other algorithms that are within the population-based methods are the swarm intelligence algorithms. For example, the particle swarm optimization method that is inspired by the social behavior of a flock of birds or school of fish locating food. So in this case, each individual that represents a feasible point is modeled by a position and a velocity, and the velocity updates are influenced by the overall trends towards optima, similar how a flock of birds move together in the air. And they introduce minimum distance constraints between the individuals, and that allows us to avoid prematurely converging towards a local optima. We can also mention the ant colony optimization method that is inspired by ants. Here, ants are the feasible points and they move individually, but as they move, they leave a trail of pheromones. And the ants can sense these pheromones within the pheromones that are close enough for them, and they provide the feedback on good locations, and they may change the behavior of the movement of each of these feasible points. And finally, we have the artificial bee colony algorithms that is inspired by how bees behave to find food. So bees are divided into groups. The employed bees look for food sources. So each of the employed bees correspond to local search. And then a second group of onlooker bees choose their food source given the information that the employed bees give. And then this process is iterated. So these are the sources that we've been using for our presentation. And that's it for us. Thank you for your attention.